Our world is becoming more complex and mysterious, with some pessimists arguing that scientific progress and society itself will soon come to a standstill due to information overload. I don't think this is a serious cause for concern. As science advances, more and more systems are being discovered in nature. And regularities, scientific achievements lead to the fact that there are fewer and fewer facts that seem to us disconnected. There's no need to record the fall of every apple, because thanks to Isaac Newton, we understand how gravity pulls everything from apples to spaceships to the Earth. The scheme of behavior of the simplest building blocks of our world of atoms. We can understand and calculate the laws and forces that govern them. Universal atoms behave the same everywhere, both on Earth and on the most distant stars. These basic phenomena have been studied by us in sufficient depth for engineers to be able to develop the mechanical creations of the modern world. From radios to rockets, our understanding of the Earth has changed under the influence of great generalizing ideas. For example, the theory of continental drift helps us to unify a number of geological and ecological models throughout the planet. Charles Darwin's greatest insights, the revolution through natural selection, reveals the underlying unity of the entire system of life on the planet. Whatever there were individual human lives, our environment is neither chaotic nor anarchic. There are models in nature. Models permeate everything, from the behavior of people, the growth of cities, the spread of epidemics, to the development of technologies such as computer chips. These laws and models, great achievements of science, talent was needed to detect them, and in some cases genius, but it is not so difficult to grasp their essence. We are all able to appreciate music, even if we do not know how to compose or reproduce scientific ideas. Science is now invading our lives more than ever. Many political issues, the energy of health, the environment, are scientifically motivated. The way science is applied, important decisions should not be made by scientists alone, but should be the result of broad public debate. But for this to happen, we all need to learn to feel the key scientific ideas. Beyond their practical usefulness, they must become part of ours. Unification theory is one example, which is string theory, which explains how everything in the universe is connected. Great scientists have spent years trying to develop a theory of everything. Unlike the homegrown theories that we all like to come up with, scientific theories are supported by accurate data obtained from carefully designed and controlled experiments. The theory in the science of creation is logical. It reflects the most accurate and experimental observations and a profound understanding of how the world works. However, a scientific theory is not at all obliged to embody absolute truth. As long as it only reflects the state of our knowledge, there is always the possibility that a new piece of the obvious will come to the surface to refute the theory and sending the theorists back to the starting point, one example of which is our vision of the solar system. In the 2nd century AD, the Greek philosopher Ptolemy developed the theory that the Earth is at the center of the solar system. It was in the early 17th century, the Italian astronomer Galileo Galilei began to monitor the heavens with a newly invented telescope, which made observations of the solar system much more accurate than observations with the naked eye. Since then, many observations, including space research, have confirmed the heliocentric model of the solar system. Other failed theories include the flat Earth theory, the phlogiston theory, an early attempt to explain the origin of fire, and the so-called intelligent design theory. The principle of least action. The essence of this theory is that actions are performed in the way that requires the least effort, so that a ray of light will travel in a straight line because it is the shortest path between 2 points. If you throw the ball, it will go to the center of the Earth. It is not known exactly who put forward the principle of least action. But if you think about it a little, your everyday experience will probably give you this idea as well. And yet in the 18th century this question was a matter of controversy. Some of the greatest scientists in mathematics, such as Leonhard Euler, Purdue, Gottfried, Leibniz, and Voltaire, argued about who first came up with this idea. At that time, it was important to give rise to such ideas since they led to the creation of equations describing the motion of bodies under the influence of forces. They also led to the creation of equations describing the motion of bodies under the influence of forces, to the concepts of potential and kinetic energy, the principle of least action. Unlike the rest of the theories, the principle of least action is just common sense. Motion in nature always chooses the simplest and shortest way. When Isaac Newton sat down and thought about how objects move, he developed three laws that have become so familiar to us that they seem to be self-evident. First, he stated that a body has inertia. That is, it can resist a change in velocity. Its motion, inertia, means that the body remains motionless until you give it a push. In the same way, moving objects continue to move unless something stops them or accelerates them. Secondly, the mass of a body determines what effect a certain effect or deficiency will have on the motion of the body. Its third law, the most famous, is that every action has an equal force and a backward reaction. If I push you, it will feel the same push in response according to the following principle: space rockets and jet engines work when exhaust gas is pushed out of the nozzle in the tube. The engines get a push forward. That's why you should be careful when getting out of the boat. Moving forward, you will certainly push the boat back. If you don't take this into account, then you risk ending up in the water. The laws of motion are all that is needed to describe how bodies move in everyday life. Newton's idea was made possible in the future to travel to the moon only for the invention necessary for this rocket's 300 years gone. The law of universal gravitation, this description, one of the fundamental forces in nature, belonged to the greatest achievements of science. Isaac Newton formulated this law in 1687. As a fragment of his ingenious principle mathematics 3-ton description, the science of mathematics, the law of universal gravitation states that everything that has mass, that is, everything that consists of ordinary matter, has mutual attraction. This extension depends on the mass of two objects, the distance between them, and the constants known as gravitational constantly. One of the main ideas of this theory was that the forces of gravity adhere to the inverse square law, which means that the attraction between two bodies decreases with a value equal to the square of the distance between them. Newton's formulation of this law was so precise that it immediately explained the motion of the planets, and it also made it possible to launch rockets into space after Einstein put forward the theory of relativity and used it to explain some anomalies in the orbits of the planets. It became clear that Newton's law is not the last word on the subject of gravity. However, it is almost universally accurate if applied by the gravitational attraction that we encounter in everyday life. Large or small, everything falls to the earth with equal probability, as you could see if you were sitting on a beam of light. Such a question Albert Einstein asked himself as a boy. The answer he found? The theory of relativity destroyed the ordered universe described with Sir Albert Einstein was born in southern Germany in 1879. His father Hermann was an unsuccessful entrepreneur. When Albert was left alone in Germany to study, and his parents went to work in Italy, he dropped out of the gymnasium. Despite the lack of school education, in 1896, he got a place at the Technical College of Zurich. Einstein continued to study a lot at home, and his attendance at the college left much to be desired. After graduation, Einstein's bad reputation prevented him from pursuing a teaching career. He began to work in the patent office in Bern and in 1903 married. The married simple work left him a lot of free time to think about physics. A year of miracles in life. Einstein became the year 1905. He published 4 papers, one of them on the relationship between light and electricity, which won him the Nobel Prize. Another became the starting point for the theory of relativity. 10 years later, Einstein published the general theory of relativity. This theory combined his ideas about energy, mass, and gravitation into a single concept called space-time. His life was shaken by the World War and personal problems, but Einstein continued to work. His main goal was to connect relativity with theories about atoms, having created a single unified theory of everything. This work remained unfinished after Einstein's death in 1955 and remains incomplete in itself. Enter the sea. Expose your body to the waves, and you will feel how much energy they contain is amazing. But they carry energy in completely different ways. Some waves, such as marine and sound, physical, move particles of water or air or some other medium, and through which these waves pass, are of 2 types. A sound wave is longitudinal if it creates vibrations that move air parallel to the direction of travel. Waves, transverse waves, such as electromagnetic waves, oscillate in a direction perpendicular to the direction of their Polaroids and sunglasses are effective because they block transverse vibrations moving in a certain direction, e.g. up and down. Any light waves oscillating in a different direction, e.g. from side to side, passes through unchanged. If the light were a longitudinal wave of the Polaroid and the lenses would be absolutely useless. Most of the wave theory was developed in the 19th century, when pioneers such as Thomas Young showed how waves can be affected by waves are. Reflected certain materials are refracted when passing through the boundary between two media or scattered by passing through a narrow opening. Waves are everywhere in the ocean, in the air, and even in the vacuum of space. Wherever they are, all waves have a wavelength, a distance from the beginning of one phase to the beginning of another. If a wave travels at a speed of 1 wavelength per second, then it has a frequency of 1 Hz. A wave in the ocean can have a frequency of 0.2 of a Hz, and a light wave has a frequency of about 500 trillion Hz. If you want to understand how heat moves, you should master the thermodynamics of this theory is governed by 3 laws. 1 states that whatever happens, all the energy in the universe remains unchanged. Gimme words: you cannot create or destroy energy, you can only convert one form of energy into another. 2nd law states that the entropy of a closed system is constantly increasing. Entropy is a part of the internal energy of a closed system that cannot be. As the clock spring unwinds, there is less and less force left in it to keep the clock ticking, and the entropy increases as the potential energy of the spring is slowly transferred to the hands as kinetic energy, and some of the energy is lost as heat due to friction in the mechanism. The 3rd law states that as the temperature in the system tends to absolute zero, the lowest possible temperature is minus 273.15 of a degree Celsius. All natural processes stop and entropy reaches a minimum. As a result, it is impossible to reach absolute zero, because no processes can bring you there. According to the theory of thermodynamics, the refrigerator does not add cold to your food, but takes away from them and into heat. It does this by squeezing the liquid in the tubes on the back wall of the device. The aerosol becomes cold when you use it. The refrigerator also works. The expanding liquid turns into a cooling gas, and then the compressor turns the gas back into a warm liquid. Electromagnetism is an incredibly powerful idea. Without it, our life would not know this. What happens if you combine electric charges, motions, and magnetic fields? Move a metal wire within a magnetic field, and an electric charge rushes into this wire. This is how we produce electricity. On the contrary, direct an electric current through a wire, and the movement of electric charges will create a magnetic field. This is how we create electromagnets that drive most doorbells and charge particle accelerators. The 3rd option is to run an electric current through a wire in a magnetic field. The wire will start moving. This idea made it possible to create an electric motor in your kitchen blender and an electric drill. The creation of the theory belongs to the Scotsman James Clerk Maxwell, who was the first to write down an equation describing the complex interactions of electric and magnetic fields. It turned out that the equation an unexpected component was required: the speed of light. This discovery led to the understanding that light and radiant energy can be thought of as moving vibrations in electromagnetic fields. These moving fields have become known as radiation. Astoundingly, but the flow of invisible particles and the influence of an invisible force field can energize everything from a toy car to a super powerful computer. An electromagnet is a magnet that has received energy from an electric current, so it can be turned on and off. Such magnets are used in an electric motor. Their Einstein theory of relativity is the most accurate description of how matter, energy, space, and time interact. Theories are actually 2: special relativity and general relativity. Special relativity appeared when it stated that nothing can move faster than the speed of light. It also showed that the flow of time is different for people traveling at different speeds. According to this theory, if you divide, the special theory of relativity also gave rise to the famous equation I equals mc squared, which describes how matter can be converted into energy and vice versa. The atomic bomb and nuclear energy were created on the basis of this equation. Proposed by Isaac Newton, it describes time as a dimension that is the same as the 3 dimensions of space, and unites them all into something called space-time. Everything is relative. We often say these words, but we don't fully understand how true it is. Even time, mass, and space are related. According to the theory of relativity, the faster you move through space, the slower you move through time. If you reach the speed of light, time will stop completely. Atomism was originally proposed in the 5th century BC by the Greek philosopher Democritus, who believed that everything in the world was basically made up of combinations of small, solid, and invisible particles. He called these particles atoms. and suggested that they come in different shapes and sizes, but all are made of the same basic material. Modern scientific theories of matter state that the vast variety of substances we observe in the universe is made up of combinations of different chemical elements. These elements are indeed made up of trillions of identical particles or atoms. The internal structure of the atom is characteristic of each element. So the hydrogen atom has a different structure than the gold atom. The modern theory of atomism began in the early 19th century with the work of the English chemist John Dalton. However, it was not until 1905 that Einstein mathematically proved the existence of atoms. A few years later, Ernest Rutherford became the first to look inside atoms as part of an experiment in which he bombarding alpha with particles from a thin gold leaf. He discovered that each atom consists of a tiny, positively charged nucleus surrounded by empty space, in which even tinier, more negatively charged electrons orbit around the nucleus. Everything you have ever seen, can see, and will see in the future, consists of a handful of atoms, even yourself. This is an incomprehensible but incredibly powerful theory of the subatomic world, in which everyday concepts of force and motion no longer apply to the usual ones. Instead, we need a new kind of mechanics based on quantum rules. This idea was first developed in the early 20th century by the German physicist Max Planck, who proposed that energy comes in tiny fragments called quantums. In the 1920s, work on this theory was continued by Albert Einstein, Niels Bohr, Paul Dirac, and Werner Heisenberg. However, despite its huge success, quantum mechanics remains shrouded in mystery because, unlike other scientific theories, no one doesn't know exactly how or why it works. It makes some predictions about the microscopic world, and they completely defy our common sense. For example, it explains how an atom can exist in more than one place at the same time until we check exactly where it is. It also states that an electron can rotate clockwise or counterclockwise at the same time, until we measure it. Quantum mechanics states that the same subatomic particle can Heisenberg's uncertainty principle. This theory of how quantum objects such as atoms and smaller particles inside atoms behave was developed in 1927 by Werner Heisenberg and named after him. According to this principle, we never know exactly where an electron is located, although at the same time we know exactly how fast both things move. Its speed, or position is essentially possible to measure infinitely accurately if we sacrifice the value of another quality, and the point is not in our lack of understanding of how nature works, and not in the smallest size of the electron, but in the fact that electrons are simply like that. In fact, it has nothing to do with us. The electron itself does not have a precisely defined position and velocity. The best we can do is to determine the region in which a given electron is most likely to move. The uncertainty principle also affects such concepts as energy and time. We can measure the exact energy of a particle, unless we ask at what point in time it has that energy. And conversely, if we determine the exact time of measurement, we have to give up all hope of knowing how much energy it is. According to the uncertainty principle, by measuring subatomic particles, you can only get a limited amount of information. In the mid-1930s, Austrian physicist Erwin Schrödinger proposed a thought experiment to show how crazy quantum mechanics is. He proposed to take a box and put a cat in it, some deadly poison, and a source of radioactive radiation. According to quantum mechanics, we cannot say until we have checked whether the radioactive atom has decayed within a given time. So we must describe it both as having decayed there and how, without parting, only after testing we will make it be either one or the other inside the Schrödinger's box. The experiment is designed so that any decayed particle there would have released a particle that triggers the release of poison and kills the cat. Since the code, according to Schrödinger, also consists of atoms, although trillions of atoms, it is also supposedly subject to the laws of quantum mechanics. So until we open the box and look inside, we have to describe the cat as both dead and alive at the same time. Only when we open the box do we identify everyone inside it as being in one of these states. Schrödinger used his thought experiment cat in a box argument with Albert Einstein, but he also helps us describe the workings of quantum physics. Richard Feynman and his many collaborators reshaped our understanding of quantum physics is a world of incredibly small particles that make up the fabric of the universe. Like all brilliant film scientists, was an independent, free thinker known not only for his insights, for which he was awarded the Nobel Prize, but also for his groovy game on the jar. Richard Feynman was born in New York in 1918. He was that physicists meant by them exclusively waves. While working at Princeton University, Feynman was involved in early research on atomic weapons. In 1943 and 1950, Feynman became a professor at the California Institute of Technology, where he worked with Murray Herman to describe the small force inside atoms. The lectures caught at the California Institute of Technology served as an inspiration for a new generation of particle physicists, and his books on a variety of topics impressed the general public. Feynman continued to work at the California Institute of Technology until his death in 1988. The field of physics is a region of space in which there is some physical influence on bodies. Examples of this: gravitational and magnetic fields. Hence, field theory describes how these fields behave and how bodies interact with the fields, in which one of the founders of quantum mechanics, Paul Dirac, found himself in the late 1920s, published several papers showing that quantum theory could be combined with James Clerk Maxwell's theory of the electromagnetic field, as well as with Einstein's theory of relativity. He created the first quantum field theory, which described the interaction of electrons and photons of particles of light in 1949. Several physicists in that a separate quantum field theory known as quantum chromium dynamics was created to describe the strong forces of only four and the last force of nature, the force of gravity, still manages to resist attempts to become quantum. Wang and quantum field theory applies the strange laws of quantum physics not only to solid particles but also to fields, describing the basic forces of nature. This theory is not a simple one. When two quantum objects such as electrons or photons come into contact, their quantum states, the mathematical information describing their quality, are connected or intertwined, then their destinies remain intertwined, no matter how far they are in the future, since it is easy to believe that two objects that have a common past and the time of their interaction will in some way affect the quality of each other. The result of this interaction will be noticeable later when we check these particles. However, entanglement theory can be much more. Countries in the quantum world of bodies are able to exhibit two or more incompatible qualities at the same time. For example, spinning in opposite directions at the same time. This is called superposition. Say if one photon is entangled with another, it can infect it with its superposition so that both will be in an overlay. However, by looking at one of them, we make the photon decide which path it will take. But since it is intertwined with its partners, we will make the other photon make the same choice. This will happen instantly, even if now the two photons are separated by millions of miles. Subatomic particles are bound to each other, even if they are separated by a huge distance. Will we ever be able to untangle quantum entanglement? Someday, quantum entanglement will allow an object and people teleport over vast distances. This is an attempt to describe in a single theory the workings of all four basic forces of nature and the relationship between all elementary particles of physics. Forces can be characterized by fields that convey the interaction between particles. They are known as field theories. So in 1915, Albert Einstein developed the general theory of relativity, the theory of the field of gravity at subatomic distances. Fields are characterized by quantum field theories that apply the ideas of quantum mechanics to the basic fields associated with the other three forces, the electromagnetic force and the strong and weak interactions. Now the goal of scientists is to understand whether the quantum chromium dynamics theory of the strong force field can be combined with the theory of electro-weak interactions, which describes the electromagnetic force and the weak interactions. The result will be the so-called grand unified theory. However, a successful grand unified theory will still not include the gravitational force problem and the fact that physicists still don't know how to formulate a real quantum field theory from the theory of gravitation. One possible candidate for such a theory of everything is the so-called string theory, but we are still a long way from understanding whether it is true or not. In the universe, everything is connected. That's easy to say, but it's very difficult to understand how to prove it. All the stars that we observe in the sky are part of a system called the Milky Way galaxy. The Milky Way is made up of hundreds of billions of stars, and hundreds of billions of galaxies are scattered across space, most of them in groups held by gravity. A cluster of galaxies resembles a huge swarm of bees that moves as a single unit. The study of the movement of groups of galaxies shows that over time they move away from each other. The best proof of this is the redshift of light from distant galaxies. Redshift literally The redshift of galactic light shows that each cluster is moving away from the other cluster, and center for this expansion does not exist. This is explained by general relativity as a result of the expansion of space between groups. So a long time ago, all galaxies, stars, and matter in the visible universe were gathered in one place in a grapefruit-sized clump of hot energy called the Big Bang. By measuring the speed at which galaxies are moving away from each other today, astronomers calculate that the Big Bang occurred 13.7 billion years ago. Imagine a grapefruit that weighs that much as the entire universe and is heated to billions of degrees. Since the amount of light emitted by a star depends on its mass, astronomers can weigh galaxies by measuring the brightness of stars. Since the force of gravity affects the movement of things, astronomers can weigh the universe by studying the motion of galaxies and the rate of expansion of the universe. All the bright stars in all galaxies are less than 1% of the mass needed to explain how galaxies move and how the universe expands. Study as the atoms of the Big Bang came into being. The particles that you and everyone around you are made of show that there can be about 4 times darker atomic matter in the clouds of gas and dust between the stars. It is called baryonic matter because it is made up of baryons in the atoms of large particles. It is now believed to be baryonic, and matter is about 4% the mass of the universe. The nature of the movement of galaxies shows that it exists 4 or 5 times more baryonic dark matter, which is made up of smaller subatomic particles. However, is about 74% of the mass needed to calculate the expansion of the universe. There is still not enough light from stars in the universe to calculate its weight. Most of the matter in the universe is too dark to be noticed by Earth, and huge and regions seem completely invisible. The Big Bang theory involves an event called cosmic inflation. Before the universe swelled into an incredibly hot fireball that has since cooled and turned into galaxies and stars. It was concentrated in a single point. Quantum uncertainty allows tiny blobs of energy to emerge from absolutely nothing. However, if such a bubble contains a form of energy known as a scalar field, it can act as anti-gravity, causing the bubble to expand at maximum speed until it reaches a volume of about 10 centimeters in diameter, roughly the size of grapefruit. Before the field gives its energy to the form of heat, and the anti-gravity effect ends at the end of the process. The inflationary model of the universe is a fiery clump of energy, a ball the size of a grapefruit, which continues to expand but more quietly as a result of the resulting inflation. The Big Bang theory of cosmic inflation suggests that a certain pattern of waves was imprinted in the space-time of the grapefruit stage. These oscillations provided the oscillations by which galaxies and beams of galaxies could increase by gravitational splicing as the universe continued to expand. Nothing could move faster than light, only space-time itself. During the period of cosmic inflation, the expansion of the universe broke the cosmic speed record of the universe, and if the gravitational force was slightly larger, the stars were smaller, they would use up their nuclear fuel faster and burn up before complex life forms like us could arise and evolve around them. According to the Anthropic principle, we can use the facts of our existence to predict the significance of certain qualities of the universe, such as the force of gravity. It is known that in the 1950s, astronomer Fred Hoyle used this argument to predict certain qualities of the nuclei of carbon atoms. Since our form of life depends on carbon, and without these qualities, carbon could not be created inside stars and we would not exist later. Hale's assumptions were confirmed by experiments. Then the question remains: why the universe is like porridge? The bear cub in the fairy tale, Goldilocks and the three bears are just right. Some believe that the universe was intended for us. Others believe that there are many universes. In life, there are only those that look like our place of the earth in the universe look like a bear's oatmeal. It's not too hot or too cold. It's just what it should be. Is it a pure coincidence? What shape does the universe have? Topology. It's the science of shapes and how one shape can turn into another. Don't tear. It's considered something. Canopy. It's a person who can't tell the difference between a donut and a coffee cup. If there was a donut made of rubber, you would be able to stretch it and shape it into a cup. The inner ring becomes the handle of the cup. The rest of the donut turns into the body of the cup. Most astronomers believe that the universe is infinite. However, if it were finite, it could be shaped like a very large donut. It were so, looking one way around the ring and the donut, you would see the same galaxies that you would see looking the other way around the ring in a more complex by topology. Imagine a cube in which opposite faces are connected. If you travel in a spaceship through the roof, you will return to the cube through the floor, even if the universe is finite. Observations show that its topology is not so simple at all. The study of the radiation left over from the Big Bang suggests that the universe may be shaped like a 5-dimensional 12 granny, very similar to the 3-dimensional arrangement of fragments on a soccer ball. For canopies, coffee and donuts are inseparable for them. The donut and the coffee cup have the same shape. Only the lengths and angles of their sides differ. It is believed that our universe arose when cosmic inflation occurred in a tiny part of empty space. Even today, dark energy causes the universe to expand faster and distributes matter into it in an even thinner layer. As a result, only empty space will remain. Then inflation will be able to create even more worlds in this empty space. Hence, our world is one of many arose in the previous phase of a process called infinite inflation, which has no end or beginning. So an infinite number of universes of bubbles can be created. Then there is no reason to expect that the laws of physics will be the same in every world. Some universes will be a suitable place for life, others it does not. It explains the puzzles of anthropic cosmology. It also means that there will be a world and in which every conceivable possibility occurs. In fact, the world and wherein the Civil War was won by the South and the world, and in which dinosaurs never went extinct, there may be other Earths on other worlds, similar to ours. Dark energy is accelerating the expansion of the universe. If this continues, and there is no reason to believe that this will not happen, then over time the expansion will occur faster and faster. At first, it will not affect matter directly within galaxies. Stars will continue to be born, live their lives, and die. However, when the matter from which galaxies will fade, and more matter will accumulate inside the various forms of dead stars, white dwarfs, neutron stars, and black holes. But as this happens, the galaxy beams will fly away faster and faster. The hand will disappear from sight. Our own galaxy, the Milky Way, is part of a small group called the local group. Over a couple of 100 billion years, a period about 10 times the current age of the universe beyond, eventually the cosmos will expand so fast that it overcomes the gravitational force and other forces, and material objects will be torn apart. The result of this will be a rapidly expanding cosmos, in which matter is distributed so delicately that it essentially makes empty. These are the ideal conditions for the birth of one or more new worlds. Due to inflation, it will take a few more years, to be exact, one more 11 nails, but eventually the forces that created the universe. Erotic theory owes its name to a Greek word meaning born in fire, another name for the Phoenix universe. According to this idea, our universe is one of two three-dimensional worlds separated from each other by a tiny space of mini-atomic diameter in the fifth dimension. It is actually the fourth dimension of space, but the name fourth dimension has already established time. Every point in our cosmos is adjacent to a point in another world. At the present time, the two worlds are slowly moving away from each other. In addition, each world expands by itself, igniting its contents. Eventually, they will turn into an empty, expanding space by that time of forces, and the original source will again bring both worlds together along the fifth dimension. The energy released by the collision of the two worlds will turn into matter, creating a new Big Bang, and for quantum effects, different parts of the two worlds will touch each other at slightly different times, creating vibrations that are the seeds of which galaxies grow. Then the world and move away from each other, and the whole process repeats. It happens all the time. This is the basic alternative explanation for the Big Bang, and it does not require the first phase of inflation. Give me your fifth dimensional space. Time and I will give you, in the Mumps universe, in which we oscillate back and forth with an invisible universe partner involved in the constant sequence of Big Bangs. Planets created from a cloud of particles as diffuse as smoke. This cloud orbits the sun in the shape of a disk. Like the rings of Saturn, the particles begin to stick together as they all move along the same path around the sun and often crash into each other. Eventually, they become large enough and begin to pull on each other. The forces of gravity continue to grow. The larger fragments absorb the smaller ones and become the early planets. These large fragments crash into each other, break apart, and reconnect many times until they calm down and become planets as we see them. Today, no one knows for sure why there are 4 small dense planets near the Sun and 4 large, gaseous planets farther away from it. Most likely, it was difficult for planets near the Sun to hold on to the gases that were carried by solar radiation. On the contrary, the gas giants could accumulate ice particles outside the boundary of zero temperature, that is, at a distance from the Sun where not only glacial water but also other frozen water does not melt. Giant planets grow from tiny dust particles. Planet Earth, the Sun, and the rest of the planets of the solar system arose from a huge cloud of dust and gas that slowly collapsed under the influence of their own gravity. Our planet never stands still, and even the continents are constantly drifting, moving in a slow dance on the surface of the Earth at about the same speed as nails grow. In the history of our planet, there are periodic times when the dance brings all the continents together, and then they create a giant supercontinent, until they go their separate ways again. This happened about 1 in 3/10 billion years ago when it was formed for its sake, and repeated 250 million years ago from Pangaea. The idea of the mobility of the continents is quite old. In 1596, noticing the compatibility of the coast of Africa and South America, the Belgian cartographer Abraham Ortelius suggested that America was forcibly pushed away from Europe and Africa by earthquakes, and however, it took another 300 years before the German scientist Alfred Wegener put forward the theory that the continents were constantly moving. But without a mechanism to explain how this was possible, the idea was not truly accepted until the early 1960s, by which time new geophysical evidence showed that the movement of the continents was accompanied by the expansion of the seafloor and was driven by currents in the partially molten layer under the solid Earth's crust and the uppermost part of the mantle. The Snowball Earth theory suggests that in ancient times the Earth was covered with glaciers, making it look like a giant snowball. Proponents of this theory, including the American biologist Joseph Pershing, who coined the term, believe that during the Cry period about 850,630 million years ago, the weak sun and the low concentration of greenhouse gases in the atmosphere led to a sharp decrease in the temperature of the planet. The point of the theory is the unusually low concentration of greenhouse gases, and there are a lot of options for its occurrence. One option is that the compound continents near the equator provided ideal conditions for the development of large-scale tropical erosion, in which carbon dioxide in the atmosphere reacted with rocks to create solids and minerals, as a result of which the concentration of gas in the atmosphere dropped sharply as the planet was enveloped in ice. It became difficult for it to warm up to the temperature necessary for the ice to melt, because the white surface of the planet reflected most of the solar radiation back into space. The only possibility was to increase the heat from the white surface of the frozen Earth, reflected the sun's heat back into space, maintaining a cold temperature. James Lovelock is one of the few independent scientists of our time. He has not worked for 40 years in a university or government laboratory. Direct and radical Lovelock, and scientist and inventor and visionary. His most famous theories, Gaia hypothesis, description of ways of self-regulation. It is not fully accepted by the scientific community, which has complaints about the methods by which Lovelock tested his ideas. Although this theory is very convincing, it is not known whether the Gaia hypothesis will ever become a useful tool for other scientists. James Lovelock was born in the city of Overnight north of London in 1919. He studied chemistry in Manchester until he moved to the National Institute of Medical Research in 1941. Most of his early work at this institute was related to the military. After working at the institute for 20 years, Lovelock went to work at NASA, where his knowledge was used to create detectors that could analyze the composition of rocks and the atmosphere of the Moon or another distant planet. Evidence of life on another planet is its dynamic atmosphere, with the ever-changing composition of the dead planet's atmosphere. The reflection on how life changed the Earth's atmosphere pushed Lovelock to create the theory of Gaia. Lovelock left NASA in 1964, returned to the UK, and became an independent scientist and inventor. In 1979, he published his first book under the simple title Gaia. It was soon accepted by the environmental community, but rejected by many scientists who argued that the dream is based on the philosophy of the new century. They are objective scientific research, however. Many believe that the Gaia theory has proved useful by launching a long series of studies and controversy. In 2004, Lovelock again lived up to his reputation as a freelance scientist when he announced that nuclear power was the best way to regulate climate change. This time criticism came from environmentalists. Global warming, a fairly innocuous name of climate that throughout its history of 4.6 billion years has constantly experienced sharp fluctuations in temperature. We live in a mild world ice age between the last ice age that ended about 10,000 years ago and the future ice age, usually between the days of the COVID period. The level of carbon dioxide, the main greenhouse gas that keeps the cosmic cold unchanged, stopping the sun's heat in the 1890s, the Swedish chemist Svante Arrhenius calculated that doubling the concentration of carbon dioxide in the atmosphere would lead to a 4-hour rise in the temperature of the entire planet degrees Celsius, while our planet has warmed by 74/100ths of a degree Celsius, and Arrhenius' prediction is likely to come true around the year 2100, provoking chaos and environmental degradation. Some love warmth, but global warming will not make the climate warmer and sunnier, but harsher. Prepare for strong winds and heavy rainfall. It is believed that the temperature on Earth depends on the amount of greenhouse gas emitted by industrial enterprises. The theory of catastrophes is based on the idea dearly loved by the creators of Hollywood blockbusters. The Earth periodically experiences unpredictable short-term cataclysms with global consequences. Such a picture of the world was born from the idea that catastrophes are the action of God, who sends them to people as punishment. Such ideas are borrowed from the biblical legends of Judgment Day and disasters, such as the flood of the 18th and 19th centuries. Earth histories marked by catastrophic events that occurred in just a few thousand years. Perhaps the most famous proponent of catastrophism was the French paleontologist Georges Cuvier, who linked catastrophes to mass extinctions in the mid-19th century. In scientific circles, catastrophism supplanted uniformitarianism, a concept introduced by the Scottish polymath James Hutton and propagated by the English geologist Charles Lyell. The Earth is marked by successive, ever-increasing changes, including the same physical processes that we observe now in the world around us. About 65 million years ago, most of the giant reptiles suddenly became extinct. The list of causes of this catastrophe extends from the fall of a large meteorite and volcanic eruptions to the disappearance of ferns that served as their food. The Gaia hypothesis was formulated in the 1960s by the English scientist James Lovelock, who called the Earth a live, self-regulating organism. Although this does not mean that our world is actually alive, it consists of complex, interconnected interactions between life and the physical environment. The atmosphere, oceans, polar ice, and rocks under our feet. According to the Gaia hypothesis, these interconnections work in a coherent way to maintain the Earth in the state necessary for the preservation of life. This balanced state, sometimes called homeostasis, is also inherent in the living organism itself, which is able to control its internal maintaining the status quo. In support of his ideas, Lovelock pointed to the extraordinary stability of the Earth's surface temperature over time. Despite the increase in solar radiation, he also noted the constancy of ocean salinity and atmospheric composition, despite the presence of many factors that could and should have thrown these parameters off balance. The habitability of our world continues to be of key interest and support to eminent scientists. Daisy Lovelock's world, a simple model of how life on Earth reacted to changing conditions on the surface of planet Earth, may be a rare example of a home for intelligent life. More than 4 billion years of evolution it took for our civilization to arise on a calm, stable planet orbiting a calm, stable star. The Sun is an unusually stable star, and it is reliable, a source of heat throughout the evolution of life on Earth. The Earth is protected from bombardment by comets. Jupiter, our giant neighbor, sucks in these icy bodies before they can reach us. But even under such conditions, several of the largest terrestrial catastrophes, including the extinction of the dinosaurs, are associated with the fall of comets. Without Jupiter, such falls would be so frequent that intelligent life would not have time to evolve on Earth. The huge moon is also extremely important. It stabilizes from the periodic forces of the Earth triggered by the moon within the Earth, keep it warm, and maintain the magnetic fields that protect us from harmful cosmic rays. The same forces trigger the ocean tides that played a huge role in bringing life to land. Life on Earth became possible thanks to a variety of happy events. For example, our giant moon helps us in many ways. 100 years ago, The Swede Svante Arrhenius suggested that life in the form of spores could have survived in space and spread from one planetary system to another. According to Arrhenius, randomly moving spores fly out of the planet's atmosphere and spread throughout interstellar space thanks to the weak but constant radiation pressure emitted by the light of stars. The modern version, the idea of panspermia, originates from observations of prebiotics in interstellar clouds. Apparently, some of the substances from this raw material, such as amino acids, fell on some researchers, especially the later ones. Fred Hoyle and Chandravikram Singh argued that not only complex organic substances, but even full-fledged living organisms, for example, bacteria, could develop in space on the surface of dust grains and then came to Earth through a comet that collided with it. And there is also a possibility of ballistic panspermia, when people were squeezed into space from one planet and made a journey to another planet. The discovery of meteorites on Earth from the surface of Mars means that we may have originated from Martian bacteria. Did life on Earth originate from outer space? Did Earth spores seeded life on other human planets suffering from sore throats or from algae infected with bacteria that spread through these parts of the body? The disease is treated with antibiotics. A small dose of medication prevents bacteria and infections from multiplying and almost completely disappears. However, after a few days it can return because bacteria that are not susceptible to antibiotics will take the place of the eliminated treatment. Transition from susceptible to drugs of a population of bacteria, a population unsusceptible, is the clearest example of natural selection. Action resistance is passed on to the next generation of bacteria, and eventually this trait becomes common to all members in a given population. This process occurs in all beings capable of passing on certain properties to their offspring through the process of reproduction. However, errors in the process ensure that each individual offspring is unique. Albeit in the smallest in detail, evolutionary changes usually take much longer. But the same process that changes a group of bacteria also explains the evolution of life on Earth over 3.5 million years. Natural selection ensures that life adapts to different conditions in an attempt to survive. The theory of natural selection states that species evolve to overcome difficulties in their environment. The theory of evolution by natural selection, a powerful blow to religion. It explains the emergence of complex organisms that were previously thought to have been created by the Creator, seems to benefit their possessors. When a cat eats a mouse, it uses the sensory system, the eyes, whiskers, and so on, the muscles, paws, and digestive system, all in order to survive another day. These properties are the result of natural selection, so that natural selection produces qualities that help living things. But these same organisms sometimes exhibit altruism. One individual sacrifices himself to save the rest. Altruism is contrary to natural selection, and it was previously believed that sacrificial behavior was for the benefit of the species. But no mechanisms have been found that can explain natural selection at the level of all organisms. Altruistic behavior makes more sense when you look at how it benefits the genome. Close relatives, for example, two sisters have at least several of the same genes. One sister can sacrifice in order to ensure the survival of the other. A deceased sister cannot pass on her genes, but the genes she shared with her sister will survive her death, and this will benefit the selfish genes to die in defense of the sister. The theory of the selfish gene arose in the 1960s, but the novelist Butler himself was able to express this idea back in the 19th century, saying that the egg or chicken came first. The chicken is most likely just the means by which the egg produces on the light is another egg. Professional scientists have their favorites and heroes who have served as an example for them. But perhaps Charles Darwin's theory of evolution by natural selection has done more than any other scientific work, thanks to which ordinary people have a different view of their place in the world. Charles Darwin was born in 1809 in a famous family. His maternal grandfather was Jazza, E. Wu, and Jude, who made a fortune in the mass production of fine porcelain. Darwin's paternal grandfather, Erasmus Darwin, a heavy drinker, physician, and poet in the 1790s, himself wrote a book on evolution. The mind believed that animals change their shape under the direct influence of their environment. This idea was later developed by Jean-Baptiste Lamarck and is now better known as Le Marxisme. 16 years old, Charles Darwin was sent to study medicine in Edinburgh, where he became interested in Lamarck's meme, as well as the work of the geographer Alexander von Humboldt and the geologist Charles Wiley, who suggested that the Earth was much older than it is generally accepted. That in 1831 Darwin boarded the Beagle ship for a fee, on which he made a voyage to the shores of South America, seen in 18 months of travel, led him to formulate the theory of evolution by natural selection. However, he decided to keep it secret until the late 1850s. In 1858, while working on a book on the subject, Darwin received a letter from his fellow naturalist Alfred Alice, while working in Indonesia, developed the same theory prompted Darwin to publish The Origin of Species the following year. His work blew up the scientific community. Darwin found himself at the center of an endless public debate on the subject, and to avoid it, he returned to house in Kent, where he wrote several more books, most of them on the strategies of origin and function of emotion. Charles Darwin died in 1882. We all think we know what information is, but this theory reveals its true essence and shows how to frame and communicate it so as quickly and flawlessly as possible. Now, information theory supports a host of everyday technologies, from high-definition digital television and divisions to mobile phones and barcodes on supermarket groceries. With this mathematical definition, Shannon was looking for ways to transmit information quickly but flawlessly, even in the presence of interference. The results of his research form the basis of so-called compression algorithms that allow entire movies to be recorded in DVDs or transmitted over the internet. Barcodes in the supermarket sheet, abundant, even on crumpled peanut packaging. Information theory can turn human voice, picture, or number into ciphers consisting of 2 digits, 1 and 0. These codes are easier to store and transmit compared to modern computers. A device from 5 years ago seems like museum exhibits, extraordinarily powerful with huge memory and hard drive capabilities. Our computers continue to rise while prices remain unchanged. This is incredible speed, first identified in 1965 by Gordon Moore, an article in the journal Electronics. He predicted that the number of electronic components that engineers would be able to cram into each integrated circuit in 10 years would increase from about 50,000 to 65,000, roughly speaking, doubling every year. Moore's law has proven to be remarkably reliable, and likely to remain so for at least the next decade, not least because it set the bar that microchip manufacturers aim to achieve. But eventually the laws of physics will force this law to give up. There is a limit to how small electronic components can be. Moore himself believes this will happen around 2025. Faster, better, and cheaper, and the conciseness, which deserves all respect, and for good reason. In the opinion of the 14th century English logician William of Ockham, elegant explanations are more likely to be true than sinuous and messy ones. He advised making fewer assumptions necessary to get the job done, or, as the authors later came up with the idea of shaving them figuratively, reducing them to the utmost minimum, based on the idea that nature prefers simplicity to complexity. Examples of this are not difficult to find. In the Middle Ages, astronomers, explaining the movement of the planets, tried to complicate their point of view about the Earth as the center of the solar system as much as possible, but it was enough to simply put the sun in the center and systems, and all this complexity turned out to be unnecessary. Occam's theory assumed that this heliocentric point of view was more correct, and it really turned out to be true, but it is often not so easy to find. A simple explanation, for example, whether Einstein's law of gravitation really simpler than the same Newton's law even today, attempts to turn Occam's razor into a rigorous mathematical rule run into a contradiction. Just hold on. You are the essence of Occam's razor. Realizing this, shorten in theory, leaving nothing but its basic elements. Every time we copy habits, skills, stories, songs, or any information from person to person, we are dealing with memes. The idea of memes along with scientific theories the same in itself is a meme. The world arose from theories of universal Darwinism. The idea that when any information is copied changes and is chosen, evolution must take place. The most familiar replicators to us is the gene, but in 1976 Richard Dawkins stated that a culture consists of a second replicator, and he called it memes. People copy memes, including the idea, skills, and patterns of behavior through imitation and learning. They change by making mistakes, intentionally allowing changes, or through creative combination and choosing which meme pick and transmit. Science mimetic studies how memes spread, why some succeed and others fail, and what are the implications of this for the evolution of culture in general. Some memes spread because they are useful to us or convenient, and for example, the sections of science and medicine, financial institutions, types, art and music. Others fly around like viruses, even if they are useless. We humans are tools of memes, and they use us to survive. All the thoughts in your head compete with each other. They want you to tell someone else about them. They want to get into another head and spread even further this old problem that concerns everyone from warlords to card players: what strategy to choose if we don't know what the opponent is thinking. Solution to such problems: law d'etre of the branch of applied mathematics called game theory, which, despite its name, deals with something much more serious than a fun pastime. First understanding both came in the 1920s, when mathematicians invented rules for so-called zero-sum games, where one person's gain equals another's loss. Known as the mini-maxi theorem, the rule advises to choose the strategy that gives the best effect under the worst circumstances. However, in real life, most games are not a zero-sum game, and some strategies can lead to the fact that both sides win and lose something. In 1950, the American mathematician John Nash managed to develop the mini-maxi theorem and include these non-zero-sum games in it. In order to understand why animals prefer to cooperate rather than fight with each other, and why psychologists have applied and studied the behavior of criminals in a law-abiding society, everything from war to business is a game, and game theory is a kind of mathematics that can help you win. At a party, you talk to a complete stranger, and suddenly you find that you have a common friend. You exclaim, "The world is small." Of course it is, and attempts to explain this have given rise to a new scientific in a discipline known as small world theory, which explains topics ranging from the spread of disease to the effects of globalization. At the center is the idea of networks created and interconnected for friends and neighbors to computers or multinational companies. Such networks tend to be a combination of close connections, such as families who live in a small village, plus a few occasional distant connections, such as villagers who have to travel a lot for math. Work have shown that one handful of these casual connections will be enough to reduce vast networks, turning them into small worlds, and where everyone is connected to everyone through relatively few intermediaries. Indeed, research suggests that every person in the world can be connected to another person through about 6 intermediaries. In our world, where everything is interconnected, one minor event can have major consequences affecting millions of people. You leave the house 5 minutes late and are late for train to the airport. When you arrive at the airport, you miss your flight and find out that the next flight will be only tomorrow. A 5-minute delay turned into a loss of an entire day. This is an everyday example of what mathematicians call a nonlinear phenomenon, where insignificant events do not necessarily have insignificant consequences. Chaos theory focuses its attention on similar situations, the outcome of which is often not random, unpredictable. One well-known example is weather, where nonlinear effects result in small observational errors that grow over time to the point where any hope of making a reliable prediction is shattered. Forecasters even speak of the butterfly effect, in which the flap of a butterfly's wing is enough for any prediction to undergo significant changes. Chaos theory provides the tools necessary to distinguish between a seemingly random and therefore truly unpredictable phenomenon and a topic that is rather chaotic, but there is some hope that they were predicted correctly. According to chaos theory, one tiny mistake can result in a serious event and even a catastrophe. Every living thing is born with certain properties and acquires other properties during life. Acquired properties include deformities such as scars from smallpox disease and scars from healed wounds, physical development such as increased muscle volume due to exercise, and skills acquired in the process of study, such as the ability to read. From the beginning, once human thoughts began to be recorded, some of these acquired qualities were thought to be inherited by the next generation. A frequent example of this idea was the fact that physically strong blacksmiths are more likely to produce sturdy offspring. This idea can be found in the writings of the ancient Greek philosopher Plato. In the 19th century, the French biologist Jean-Baptiste Lamarck described the inheritance of acquired qualities in his book, a precursor to Darwin's theory of the for generations. Giraffes could reach trees in search of food by slightly stretching their necks. If the acquired elongated neck of each individual animal was inherited by its descendants, over time, giraffes developed a long neck. If there is not enough grass for everyone, why not try the leaves? This is how giraffes developed a long neck. This did not happen in the way Lamarck had expected. the ancestors of man separated from the huge apes about 6 million years ago. Between that period and the period about 2 million years ago, our ancestors lived in Africa. Then the first humans, called Homo erectus, came out of Africa and settled Europe and Asia until about 30,000 years ago. Homo erectus and his descendants, known in Europe as Neanderthals, took over all three of these continents. The question is whether modern humans evolved from the species of hominids that lived in Africa and Eurasia within the framework of the idea called the multi-zone hypothesis, where we all descended from a single ancestor in Africa that spread across the globe during the second wave of migration. Wiping out native humanoid fossil evidence was mixed. Then in the 1980s there was genetic evidence if the multi-zone hypothesis is true. The gene of modern humans must have a common ancestor. In fact, the amount of difference between our genes is very small. The degree of similarity requires us to have a common ancestor. Age genetics proves that all 6.7 billion people alive today are descended from just a few thousand early Africans. The term sociobiology is yours with popular consciousness in 1975 after the publication of the book of the same name by Harvard biologist, and Wilson defined sociology biology as the biological study of social behavior. Wilson wrote about the emerging field of biological research, which sought answers to many questions. Why males and females are different? What is the function of mating systems? Why some species are monogamous and others are not? Why animal communities have this structure? For example, chimpanzee groups consist of male relatives and young females who leave home, while in baboons, it is the young males who leave their families. Sociobiology also explores the causes of such phenomena as camaraderie, altruism, territoriality, and tries to answer the question of why some species live in large groups and others have hermits. But Wilson has gone a step further in the last chapter of his lengthy book. He offers several biological explanations for human social behavior. This chapter has drawn an outcry from those who have decided that it has offended their political views. If you believe that human society tops sociobiology, think again. Bees, ants, and other insects live in large groups, but for very different reasons. The inhabitants of Olga are all the sisters who work for their mother. The queen's purpose of existence, to care for their newborn sisters, so that the queen has as many daughters as possible. Grammar, the key to understanding human language. Many species of animals have a developed sign system that they use to communicate, but they do not have subordinate clauses of moods, cases, and prepositions that make up grammar. Human language is infinitely expressive and can be used to discuss and think about abstract concepts. Where the language and grammar came from, the changes required for this were in the software of our ancestors' brains, and it is impossible to study them. However, we have two indirect evidence. The first time when human brains appeared, working the same way as ours did a little more than 100,000 years ago, and the brains belonged to the people who came from Africa and gave birth to a talkative straightforwardness called Homo sapiens. That is, us anatomically, their brains were identical to ours, which means that they had the same linguistic capabilities as they did. But the key change came later and affected not just naked anatomy, but because we use our brains. Archaeologists have discovered a lot of delicate tools, jewelry, and other objects that are about 30,000 years old. Language is what distinguishes humans from animals. Only we know how to express our thoughts. Now the only thing left for us to do is to think of what to say. Only in humans, the brain is large enough to encompass all the many ways to say the same thing, as in tattoos of a man with a devilish image of himself on one shoulder and an angelic version of himself on the other. Sigmund Freud's theory of psychoanalysis states 100 the human mind is torn apart. Our is constantly striving for a balance between the needs of the one who receives it. The central idea of psychoanalysis is that much of this conflict is hidden under the cortex of consciousness, only occasionally interrupted by a nervous tic or a Freudian slip of the tongue. Sex also plays a large role in this theory. In particular, Freud believed that the source of physical conflict is the sexual fantasies of childhood. The most famous example of this is the Oedipus complex, the idea that children lead their parent of the opposite sex and jealously wishing for the death of a same-sex parent. That I can't possibly. You will say that you have never had such desires. Your denial will be an excellent example of suppressing one of the many defense mechanisms that Freud believes we use to tame uncomfortable desires. Such psychic maneuvers will save our reputation for a short time, but can eventually distract and make the psychoanalyst's clients attest with ink blots, a technique used by the psychoanalyst patients describe the forms that they see in the spots, thus revealing their repressed emotions. If you see nothing but an ink blot, then behaviorism, from the English speech Euro behavior, dominated the science of psychology for half a century, although it ignored all notions of mind and consciousness and refused to take into account the sense of thought and desire. Instead, it focused on patterns of behavior that could be measured in the laboratory. Behaviorism appeared in 1913, when psychologist John Watson stated that the degree of human learning could be studied in the same way as Pavlov's famous dogs, which stood out at the sound. He argued that the development of a suitable, conditioned reflex can be used to turn one's children into anyone one desires. B.F. Skinner, another American psychologist, came up with the development of an instrumental conditioned reflex, in which rats are rewarded for a certain behavior and punished for a friend. And by teaching them to press levers, run through a maze, he found that praise is much more effective than punishment. A key principle for Skinner founded his own school of radical behaviorism, arguing that all our actions are determined. He also reflected on an atopic society based on the conditioning of all citizens, and Heavy Oris explains how people learn from their experiences, both good and bad. The term cognitive psychology was coined by Lyric Na and Cheese in 1967. It was an interesting transition from dominant behaviorism, limiting all research to mental processes. The new cognitive psychology studied internal mental events and evolved into a rapidly developing science of artificial intelligence. In this new science, the mind was likened to software, and the brain to the equipment of a biological computer. Human actions and decisions and thoughts were, for example, the study of the visual system of the brain showed how the information coming through the eyes is processed by the layers of eye cells, the midbrain of the sensitive cortex, and sent to the areas of the brain capable of recognizing objects or controlling actions and speech. That it is the brain or a computer. Cognitive psychologists claim that there is almost no difference, and the brain is a mechanism for processing information. By genes control most basic life functions. When they go astray, we can have diseases, from Alzheimer's to cancer, and we can pass on inherited diseases to our children. Genetics in medicine is trying to find better, if not perfect, treatments by researching the genes responsible for the disease. It sounds pretty simple. Find the questionable genes responsible for the disease, run them away, and insert a fresh copy. For a while, this is how genetics in medicine was imagined, but the reality turned out to be the reality. While some inherited diseases are the result of a single faulty gene, most diseases arise from complex interactions between a set of genes. The restoration of even a single gene has proven to be an incredibly difficult task, and to date no person has been cured of a genetic disease. Genetics has been more successful in creating drugs that regulate gene-related diseases. For example, the drug Herceptin has been created by identifying the genes involved in a certain form of breast cancer. But even such drugs have a very limited effect, and is another example of how genetics in medicine has not lived up to the hopes associated with it. Perhaps one day gene therapy will become a panacea, but first the geneticist needs to understand exactly how the DNA strand builds the human body. Knowing this, we will be able to notice when it fails and fix it. Supporters of alternative medicine, from acupuncture to yoga, consider it as a therapy that can be used alongside conventional medicine. For its opponents, this is a bunch of unproven tricks that take hold of patients. While the main burden falls on conventional medicine, there is some truth in this. Some conditions that seem to respond well to complementary therapies, such as pain and depression, are associated with a powerful placebo effect, in which patients believe they feel better after a generally useless treatment. Scientific experiments in which such treatments have been tested, and there have been conflicting results, not least because many experiences have not been adequately funded. But it cannot be denied that some forms of complementary medicines, namely acupuncture and meditation, are effective for conditions such as headaches, and stress. And there is certainly no doubt about the popularity of alternative medicine. Such treatments have long been widely used in Asian countries and Japan. To their help, regularly 75% of the population. Now their popularity is growing in the West. Alternative medicine is becoming more and more popular, although in many cases its effectiveness has not yet been proven by large-scale controlled clinical experiments. Herbal medicines are one of the forms of alternative medicine. Many patients trust them unconditionally, and most doctors scold them Once doctors chose treatments for their patients based on personal beliefs, information they received many years ago in medical schools, or on the advice of their tennis partners, sometimes this approach has worked. Sometimes not evidence-based medicine is trying to put such a solution on a more scientific foundation based on the results of carefully controlled clinical trials. Doctors can now access databases online that provide the latest information on the most effective treatments based on a review of clinical trials conducted by experts with an international. Whether they actually do so is another question. Many doctors still prefer to act on their own. Either they are too busy to read reports, or they are suspicious of the reliability of clinical trials, or they do not want to limit themselves and thoughtlessly apply proven quotation treatments. However, evidence-based medicine enthusiasts insist that doctors must always combine solid evidence with their judgments of the patient's needs. With each doctor, there are favorite medications and treatments. But where is the evidence that you are getting the best treatment? Imagine being given a pill and being told that it will eliminate the headache and your condition will improve. Although the pill contains nothing but chalk, it is the placebo effect from the Latin I will like in medicine. This term is applied to describe treatments that have no real medical effect and work. The violence of persuasion, first described in the 1920s. These days, the placebo effect is an integral part of evidence-based medicine. In clinical trials, drugs are compared to placebos. This can be a pill that looks exactly like real drugs but does not contain drugs, or acupuncture needles that look convincing and are just as convincing to the touch but do not actually pierce the skin. In a random, controlled trial, half of the patients receive the real drug and the other half receive a placebo. If both groups demonstrate the same, it becomes clear that the new drug is useless. The placebo effect is incredibly strong, and its effectiveness is even increased if the patient receives a larger pill. The pills are pink, they are white, or if they are prescribed by a respected doctor. The pill does not have to contain drugs. Thanks to the placebo effect, you think you feel better, although now you know that the effect may not be so strong. Friends, thank you to everyone who watched this video to the end. I thank everyone who supported this video with like and subscribe to the channel to not miss interesting videos on our channel in the future. I will also be grateful for your comments. Please write in the comments which theory you think is the most important for humanity. Hope to meet you in the next video.